Right, for this question, we're told to do an integration using a variable substitution. We're going to replace the variable x, which means we also have to replace the boundary conditions, and we have to replace the reference variable. Right, so to do that, we differentiate the equation that we're given, dx d theta is equal to 3 sec squared theta, which means we are able to replace dx with 3 sec squared theta d theta. That's our first step. To find the new boundary values or the replacement boundary values, we need to rearrange the initial equation. So x equals 3 tan theta would be simply rearranged to tan theta is divide the x by 3, and then we can find out that theta is equal to the inverse tan of x over 3. Right, so what we do is we then use the boundary conditions. When x equals 0, we put 0 into the equation and we get the inverse tan of 0. The inverse tan of 0 is 0, so theta is 0. And when x is equal to 3, we put it in and we get the inverse tan of 3 on 3, which is the inverse tan of 1. The inverse tan of 1 is 45 degrees, or because we're in radians, it's going to be pi on 4. Okay, I'll work down a column so you can see everything on one screen. We're going to take what they gave us, integrate from 0 to 3 of 27 divided by 9 plus x squared dx. And we're going to do some replacements now. So I is going to be equal to, we do the substitution, x is 0, theta is 0, and when x is 3, theta is pi on 4. Of course, we're replacing it to theta. Everything that is not a variable stays the same. So we have the 27, we have 9 plus, instead of x, we're going to replace with 3 tan theta, but it's squared, so 3 squared will get 9, and then we'll get tan squared theta. And the whole bottom still stays squared, of course. And we will replace the dx with 3 sec squared theta d theta. So that's given us the variable replacement. All we have to do is rearrange it so it equals what we're trying to get to. All right, so we have the 3 times 27 is going to turn into 81, and we may as well bring the sec squared theta up to the numerator as well. On the denominator, we have 9 plus 9 tan. We can factorize the 9 out, but it's still in the squared brackets, so we can get it out of the squared brackets by squaring it, and it will turn into 81, 1 plus tan squared theta squared. You can imagine that it's 9 squared out the front, which became 81, which is handy because that's going to cancel with the 81 on top. And of course, there is the d theta there. All right, so we will cancel the 81 on the top and 81 on the bottom. And 1 plus tan squared turns into sec squared. So we end up with sec squared theta over sec to the power of 4 theta d theta, which is greatly simplified, which is then equivalent to, we cancel sec squared from the top and the bottom, sec squared theta d theta, which of course, sec squared is 1 over cos squared. So the whole equation becomes the cos squared 1 divided by 1 over cos squared is 1 times cos squared over 1. And so that just turns into cos squared theta d theta, which is what we had to show. The hence part is saying use the simpler version to do the integration, but we can't integrate cos squared theta as it stands. So we reach into our formula sheet and hopefully we realize there is a formula where cos of 2a is equivalent to 2 cos squared a minus 1, which of course can be rearranged so that cos squared of a equivalent to a half of 1 plus cos of 2a. So we can do this substitution in our integration. Because the half is multiplying by the whole function, the half can come out of the integration sign. It may make things easier. I always like to take a coefficient out if it's multiplying by the whole function. So cos squared will become, well, the half is out the front, so it's going to become 1 plus cos of 2a. It's not going to be a, it's going to be 2 theta d theta. All right, that's a lot easier to integrate now. And so when we integrate that, the half stays out the front. The 1 integrates to theta, and the cos is going to integrate to sine. It will be 2 theta. When we differentiate, that would put a 2 out the front. So we need to get rid of the 2 that it would put out the front when it was differentiated. And we go to the boundaries of 0 and pi over 4. So now we substitute the boundaries in, and we're going to get a half of pi on 4 plus a half of sine, and 2 times pi on 4 is pi on 2. Of course, sine of pi on 2 is just 1. And then we're going to subtract. We better put another bracket there. We put 0 in, and we'll have 0 plus a half sine of 0. And sine of 0 is just 0 as well. So it's handy to know your trig functions. And this will become, all right, we should write it. A half of pi on 4 plus a half. Let's turn the half into 2 on 4. And so we can add those two together. Then we're subtracting 0, there's nothing there. So pi on 4 plus 2 becomes pi plus 2 on 4, and multiply by a half, you'll get pi plus 2 over 8. And we have the exact answer for the integration.